Hi everyone. So today we'll be discussing on the topic Farach's algorithm, also known as Martin Farach-Silton algorithm. Right. So let's get into the definition part. What does the definition part says here? Farach's algorithm builds a suffix array. Right. It builds the suffix array, nothing but sorted order of all the suffixes of a string in the linear time, nothing but big of n. Yep. So just remember this one. Farach's algorithm builds of suffix array sorted order of all the suffixes of a string in big of n time by recursively sorting only odd position suffixes, by recursively sorting only the odd position suffixes, then using those ranks to sort the even position suffixes. Then what it will do, then using those ranks actually, the previous step, so to sort the even position suffixes, so we'll be going with the odd as well as the even position suffixes in a single radix pass. Yeah, in a single radix pass. So we will be making use of the radix sort as well here. So just remember this one, in a single radix pass, radix word plays a prominent role here, and merging both the halves, and merging the both halves actually. That's what the Farach algorithm does here. Already the algorithm is present actually. It's huge basically. So I have already this one written the algorithm. So before hopping into the algorithm part or the coding part, let's do one thing. Let's discuss the approach, or let's go with the algorithm explanation. Then we can just come to the coding part, right? If everything goes well, then we can discuss the complexities for the code that we have written. Before that, as usual, let's discuss the algorithm first, or let's discuss the approach first. Yep, let's do that. So let's do one thing. Let's move on with the algorithm part. Yeah, we'll be going with the example banana here. So we'll be considering the same string actually. Banana followed by the unique terminal, nothing but the dollar actually. Banana. Yep. So this is fine. The first step, we will be compressing odd position pairs into the new strings. First, what we'll do, we'll compress odd position. So see here. So it will start. So this is zero index, right? 0, 1, 2, 3, 4, 5, 6 actually. Odd is nothing but 1, 3, 5 over here, right? Which is a. Mm, yeah, which is A as well as the A. So A is present thrice, right? In the odd position. So we'll compress the odd position pairs. So we'll be going with the pairs, not only the words, we'll compress the odd position pairs into the new strings, right? Odd positions are indices 1, 3, and 5. As I've said, odd positions are indices 1, 3, as well as the 5. So this is fine. What we'll do, we'll form the pairs. When I say we'll form the pairs, so we'll be going with the 1, 2, 3, 4, as well as the 5, 6, right? So pairs in the sense we'll be going with the two letters. But I have mentioned, so already mentioned here, nothing but pairs. So it has to start from the odd, and it should have one more character. So odd, we have A followed by the A, right? So next to the this one we have the second index N. Next to the third index we have the fourth index, nothing but N. And next to the fifth index we have the sixth index, nothing but the dollar. So this is nothing but AN as well as the A dollar. So we form the pairs AN as well as the A dollar, right? So we'll rank them now. So the new string that will be formed is nothing but 2 to 1. So when we rank them, the new string that will be formed is nothing but 2 to 1. So 2 to 1, why it is this one 2 to 1? So here we have to rank them, right? So we have to compress the odd position pairs into the new string, right? Or we'll be adding the positions. So we'll be adding the odd positions basically, that are indices 1, 3, and 5 in the example that we have considered for the banana actually, right? So this is fine. After ranking them, the new string that we got here is nothing but 2 to 1. Yep, 2 to 1. So let's move on with the second step here. So we'll recurse on the compressed string. So recursion is one of the very important parts of the Farach algorithm. Just remember this, we will be recursing on the compressed string, nothing but 201. Yep. So we'll recurse on the compressed string. Now this becomes 201, right? So 201, after getting this one, this is nothing but the index that I have mentioned. So after doing that, we'll map back to the original odd positions. What we'll do, we'll map back to the original odd positions. So suffix array of the odd suffixes is nothing but 513. Suffix array of odd suffixes is nothing but the 513. Rather than mentioning the index, actually, I'll show you the this one. What do we call? By considering the example, so we will be discussing the same later. So you'll get to know that one, this one, even clear, right? So here we'll sort even the position suffixes. Again, we'll be going with a sort, this one, radix sort as mentioned earlier. So we'll sort even position suffixes using the odd rank. So now we have got the odd ranks here. after, so with the help of the step 1 and the step 2 actually, finally we have concluded with this thing actually. Suffix array of the odd suffixes is nothing but we will be going with the 513. So we will sort even position suffixes using the odd ranks actually. Even suffixes start at 0 to 46. Here you can clearly see, right? 0 nothing but the character B, 2 nothing but the character N, 4 nothing but the character N, and 6 nothing but the unique terminal dollar, right? So sort, we will be sorting even position suffixes using the odd ranks. Yep, that's what we will be doing. Even suffixes start at 0 2 4 6 as per the example that we have considered, and we will be pairing each even suffixes nothing but s of 2i with the rank of its odd neighbor, right? So we will be, what we'll be doing, we'll be pairing each even suffix nothing but s of 2i with a rank of its odd neighbor nothing but s of 2i plus 1. This is for the odd actually. Yep, rank of its odd neighbor nothing but s of 2i plus 1, the next one actually. That is the reason we'll be going with the s of 2i plus 1. Yep, radix sort would be, so instead of 0 to 46, this time it would be, after the radix sort, applying radix sort, it would be 6042, right? It would be 6042. Yep. So this is fine, I believe. It's as simple as that. This states that we will be sorting even position suffixes using the odd ranks. Yep, odd rank that we have got here is 513. Each suffixes start at the 0 to 46 because of the example that we have considered for the banana, right? So 0 to 46 will pair each even suffix nothing but s of 2i with the rank of its odd neighbor. 513 that we have got s of 2i plus 1. So when we apply the radix sort, we get 6042. Yep, 6042. Next, let's move on with the fourth step here. We'll compute the this one LCP arrays for both halves, right? Odd half as well as the even half. We'll be computing the LCP arrays for both the halves, nothing but the odd half as well as the even half. So this will be big of n via Cartesian RMQ. So along with whatever we had discussed till now, whether it may be radix sort, whether it may be Euler, whether it may be this one, what do we call even pair, as well as the odd pairs, we will be computing the LCP arrays using the Cartesian RMQ, right? So we will be making use of the Cartesian RMQ as well. Yep. So there will be many things we'll be making use of, but on the this one Farach algorithm. Yep. So this is fine. We'll be computing the LCP arrays for both halves. Nothing but it will be big of n via Cartesian RMQ, right? LCP between the consecutive odd suffixes uses RMQ on the recursive LCP. And one more thing, we'll be going with the recursion here. For the merge part, we will be making use of the recursion. You will get to know that one when we discuss about the code actually. Yep. For now, we don't have to worry that much. Again, LCP between the consecutive odd suffixes that we consider uses the range minimum pair is nothing but the RMQ on the recursive LCP array. Yeah. Uh, Recursive LCP array. So LCP between the consecutive even suffixes uses RMQ on odd LCP array. Again, this point you have to remember this one. LCP between the consecutive even suffixes uses the RMQ, right? So this part is very important. Again, LCP between consecutive even suffixes uses RMQ on odd LCP array. So this is fine, I believe. Next, let's move on with the step 5. So we'll merge the two sorted halves, nothing but the odd as well as the even half. So then we will use the LCP bounds as credit. Then we'll be making use of the LCP bounds as credit. So each comparison is big of one amortized, right? So that each this one comparison is big of one amortized. Then we will find the result. Right. So suffix automaton for this one actually 6531042, and the LCP would be this one. What do we call? A suffix array, sorry, not the suffix automaton. So this one LCP is nothing but the 013002. The result would be this one. Yep. So here, let's see the same thing actually, whatever we had discussed in the theory part. Let's apply the same thing for the example banana. We will understand this one even clear, or else we'll not get to know anything correctly, right? So first, we are going with the example banana here. So this is the original string with the indices. So this one will be 0, 1. So let me mention over here 3, 4, 5, 6. First step, what we'll do? So we'll consider the odd index, right? So we'll rank the pairs actually. Before ranking the pairs actually, we will be considering the odd index, the step 1 actually, if you remember. This one will compress odd position pairs into the new string. Odd positions are indices 1, 3 as well as the 5. So we have to consider the pairs right here. So odd position 1, 2, then the next odd position was 3, 1, 3, 5, right? Then 3 and 4 for the pair, and the next odd position 5, nothing but 5, 6. So we have got AN here, AN as well as the A dollar. So this is fine. Next we have to rank the pairs. We have and the compressed one becomes here this one, 2, 2 as well as the 1, 2, 2 as well as the 1, right? So this is fine, I believe. Yep. Then the second step is we have to recurse on 2 to 1. Yep, we have to recurse on the 2 to 1. So this is nothing but the on the odd suffix array, right? So we have to map back to the original positions. That's what we saw in the step 2. We have to map back to the original positions, right? So we will be considering position 5, position 1 as well as the position 3, right? Position 1, position 5, position 1 as well as the position 3, we can just write it in this way. As we are going with the pairs actually, position 5, it's A dollar, less than position 1, it consists of ANA, right? It's less than this one, ANA dollar, right? So that is the reason we have got the output here, position 5, position 1 as well as the position 3, right? So we are mapping back to the original position. So this becomes 513. We have already discussed this one in the step 2, right? So nothing but at the position 5 we are having A dollar, position 1 we have ANA, followed by the dollar, and final we have the ANA unique terminal, nothing but the dollar. So this is fine. Next, let's move on with the third step here. So we will apply the radix sort, right? We will be going with a radix sort, or we'll be applying the radix sort, right? Radix sort even suffixes using s of 2i and the odd rank 2i plus 1. That's what we had discussed within the third step. Now, after applying the radix sort, we got 6042, if you remember. Position 6, position 0, position 4, position 2. So if you don't have the idea on the radix sort, if you don't have the idea on the Euler, if you don't have the idea on this one, whatever we are discussing, whatever the terms that I'm saying, if you don't have the idea on the LCP, RMQ, every algorithm and every concept that we have considered within the 150 based algorithms playlist, you have to know the algorithms pretty well. I'm not saying you have to mug up the algorithms, you have to have the idea on the algorithms. If you see the algorithm, you have to remember everything. Yep, how it works. If at least if you glance and if you go through the algorithm, you should be able to this one recall everything that you had um, already this one studied, or this one whatever you have went through, whatever the algorithms that you have went through. If you don't know the concepts, if you don't know the this one RMQ, if you don't know this one, what do we call LCP, if you don't know Cartesian RMQ, then so we have discussed everything within the 150 best algorithms playlist. You have to know the concepts pretty well to understand this one again. So we will be applying the radix sort, or will radix sort even suffixes using s of 2i on the odd rank s of this one 2i plus 1 basically. Yep. So after applying the radix sort, we will be going with the position 6, position 0, position 4 as well as the position 2 here again. So this one we had already discussed, right? So this one unique terminal, nothing but the dollar, less than banana followed by the unique terminal, less than followed by this one na followed by the unique terminal, less than NANA unique terminal, or the dollar, right? So this is fine. So what we will do, we'll LCP via this one Cartesian RMQ on the recursive LCP basically, which helps us to get the big of 1 per query. Yep. So what we'll do, so we'll LCP via Cartesian RMQ on the recursive LCP. Yep, on the recursive LCP again, we'll be going with the recursion for the merging part, so that you'll understand when we go through the code, actually algorithm, right? So LCP via Cartesian RMQ on the recursive LCP, so that we get big of 1 per query, right? So in the definition part, we had discussed on the same thing, that we that would lead to big of n actually. So if I say here, mm, so here we did not discuss, I believe. So 1 second. So we had discussed here itself, I believe. It is 1 second. Anyways, Here in the step 5, I believe. Sorry. So each comparison is big of one amortized, right? So we'll be merging the two hubs. We'll be using the LCP bonds as credit, so that each comparison is big of one amortized. Sorry, I got confused. So this is fine. Anyways, will LCP via this one Cartesian RMQ on recursive LCP nothing but big of 1 per query. So odd LCP is nothing but 1 3, and the even LCP that we'll be getting is nothing but 0 0 2. Odd LCP is nothing but 1 3, and even LCP that we are getting is nothing but 0 0 2. So 1 3 between the position 5 1. So we are going with the this one 5 1 3, right? So we got 1 3 5. After the second step, actually we have to go with the 5 1 3 basically. Yep, so this one I'm speaking of. After recursing on 2 to 1, basically we went with the 1 3 5, the odd numbers, actually the first step. Then the rank pairs and the compressed ones are 2 to 1. Then we are recursing on 2 to 1. So we'll map back to the original position. At that point of time we get 5 1 3, the same thing. So odd LCP is nothing but 1 3. So between the position 5, position 1, as well as position 1 and position 3, right? So the even LCP is nothing but 0 0 2. Here between position 6 and position 3, position 0 as well as the position 4, position 4 as well as the position 2, right? So you can just pause the video and have a look into it. Odd LCP 1 3, even LCP 0 0 2. So here between position 5, position 1, position 1, position 3, as well as for this one 0 0 2, position 6, position 3, position 0, position 4, as well as position 4, as well as the position 2. So now let's move on with the fourth step. Fourth step is nothing but the even, right? Sorry, not even, merging basically. So we have to merge even and odd halves using the LCP credits. So that's what we have to do accordingly with the algorithm. Yep, what we had discussed earlier. So we have to merge even as well as the odd halves using the LCP credits. Here suffix array nothing but 6 5 3 1 0 4 as well as the 5 that we are considering. So this is nothing but the final suffix array. So to get the final suffix array, what we have to do, we have to merge even as well as the odd halves using the LCP credits, right? This one we are going with a suffix array 6 at the position 6, or at the index 6 we have got dollar or the unique terminal. At the this one suffix array, when at the index 5 we have got the a dollar, right? So you can just write it over here and you can just check actually. Yeah, we are going with the example BANA dollar, right? At the SA3 or the suffix array equals 3. So 0 1 2 3 here, this starts from here A N, this one ANA followed by the unique terminal, nothing but the dollar. Same goes with the 1 from 1 0 1. We have to consider all the thing ANA, this one followed by the unique terminal. Same goes with 0 4 as well as the 5. Similarly, when we start from the 0, we get the entire this one string BANA dollar. When we start from the 4 0 1 2 3 4, actually we have to start from N. So NA followed by the dollar. And when we start from the 5, it's just A as well as the unit. Yeah, it's just for the suffix this one. Actually, this time actually we have to go with 1 second. So actually this has to be 2, not 5. I have mentioned it wrong here. Suffix array 2. So when we start from the 2, it has to be, we have to start with the N basically. N followed by the ANA unique terminal, nothing but the dollar. Right, so this is fine. So we have successfully merged even as well as the odd halves using the LCP credits here. Nothing but that would lead to final suffix array. So finally, the LCP array between the consecutive suffixes is nothing but LCP equals 0, 1, 3, 0, 0, 2. So this is the output. LCP nothing but 0, 1, 3, 0, 0, 2. And suffix array, so this one is 6. I'll just write here SA or the suffix array that we have to get 6, 5, 3, 1, 0, 4. Finally, this is 2. This is not 5 actually, this is 2. Yep. So this is the output that we need to get accordingly with the algo. Yeah, this is the output that we need to get accordingly with the algo. I hope this part is completely clear. So this is it for the algo, right? So I have just considered the example actually, banana followed by the unique terminal dollar, so that we understand this one even clear, right? Better actually. right? So this is fine, I believe. We are done with the algorithm part. So let me delete this one. So let's move on with the coding part. So let's try to articulate the exact same thing in the form of code. Let's do that one quickly. Yeah, let's do it. So let's move on with the algorithm part here. So first thing here, yep. So we are going with a plus minus RMQ. What is plus minus RMQ? One second. Just give me a second here. So what we'll do, we'll go with the this one. One second. Yeah. Fisher-Hewn structure. So we call it as here Fisher-Hewn structure. So what it does basically, so this will give us big of n build. Yeah. So this will give us big of n build, big of one range minimum query as per the discussion earlier. So this will give us big of n build, big of one range minimum query. So this is only valid on the arrays where adjacent values differ by exactly plus or minus one. Right? Exactly plus or minus one. So we'll be going with a Euler to depth arrays. Satisfy this by the construction. Basically, just remember this, the first method that I'm speaking of, that will be making use of plus minus RMQ. This is nothing but Fisher-Hewn structure, because we get the big of n build as well as the big of one range minimum query, right? So you have to remember this one at any cost. Let me delete this one. Yep. Now the first thing here, so we are going with the different variables here, right? So we are going with the different variables. Let me scroll this one. Yeah. So we are going with the different variables here. So nothing but here. So A is for the reference to the plus or one, plus or minus one, this one array actually, plus or minus one array. So the variable that we are making use of here. So next we have NB as well as the NB. N is nothing but the length, B is nothing but the block size, and NB is nothing but the number, right? So we'll be making use of these variables as well. And we are going with a bmin index, nothing but it is the global index for the mini. Yep. So we are going with a global index for the mini. So this is fine, I believe. And next we are going with a B type actually. Yep. Next we are going with a B type. After the bmin index, we are going with a B type. B type is nothing for the bitmask. This one, bitmask encoding, and one second. Yeah, bitmask encoding, and so this will be actually B type, whatever we are going with. So B type is nothing but here in this case bitmask encoding the plus or minus one rise or fall pattern of the block B. That is the reason we'll be making use of the variable bit type. Then we are going with a slog. Slog of I is nothing but the floor of, we'll be going with a math function for that. We'll be going with the floor of log2 of I, right? So this is nothing but the pre-computed version for the sparse table lookup. So basically, this one Farach uses the this one, what do we call, sparse table. And just remember this one, we will be strictly making use of the sparse table. So this one you have to remember. Yep. So the slog variable that we are making use of here. So this one slog, what it does. So this is nothing but the pre-computed value for the sparse table lookups, and we are going with a sparse as well. The variable sparse here you can clearly see sparse of ji. So this is nothing but the, we'll be making use of it, this variable, nothing but it acts as the block index with minimum over 2 to the power of j blocks starting at the I. If you know the sparse table, you will be knowing what I'm speaking of actually. Finally, we'll be making use of the pre, this one variable pre here. Pre is nothing but it's the local index of the minimum for the range I to j, right, of the pattern type. Next, we are done with this part. Next, let's go with the this one. What do we call the constructor part, where we will be initializing certain things. Yep. So n, we are initializing this one to the array. We are just storing the reference. Then we are going with the total number of elements here. Then we are going with the block size. B is nothing but the block size. We are going with the math.min here. This part is nothing but we are going with a block size log that is almost equivalent to log n by 2, right? Log n by 2. So this part I'm speaking of. Finally, we are going with a NB, right? So finally, we are going with the NB. So we will be going with the ceiling division. So we'll be seeing how many blocks fit basically. Ceiling division is nothing but n plus block minus 1 by block. That's what we have given here, right? So let me delete this one. One second. Yeah, let me delete this one. Next, we have went with a bmin index. So let me scroll this one over here. So this is fine, I believe. Next, we have went with two variables here, bmin index as well as the b type, right? So what is bmin index as well as the b type? So this is one entry per block, and this one is nothing but one bit mask per block, these two things, bmin as well as the b type. Next we are going with a for loop here, right? So next we have written actually nested for loops. You can clearly see here the first for loop here, the main for loop. So we have to iterate over every block that we are considering. So that is the reason we are going with the, see here, b equals 0, b less than nb, as well as the this one b plus plus. So this is fine, I believe. So within the for loop, LO, for the LO, we have went with a B into B, nothing but first index of the block B. For the high, LO, nothing but the low. And for the high, I have went with math.mun, right? So what is this high? We have assigned it for the math.mun of n comma LO plus B. So this is nothing but we are going with a one past last. So this will be clipped to n basically. Yeah, this will be clipped to n, right? So this is fine. The next step, we are this one. We have to start, or we are assuming the first element is the minimum here. First element is the minimum. So this is fine. Next, we are going with one more for loop. So we have to scan rest of the block. That is the reason we are going with one more for loop here. Within that for loop, we are updating the minimum index if the smaller element is already found. Suppose if the smaller element is already found, then we have to go with the updation step, nothing but we have to update the minimum index. That's what we have done here, right? So this is fine. Next, we have initialized t to 0, nothing but the why we have initialized the t to 0 here, because the bit masking starts from the 0, right? So bit mask starts from the 0. That is the reason we have initialized t to 0. Next, what we are doing, we have to look at each consecutive pair within the block. So if you remember, we have went with an as well as the a dollar. We have to this one, what do we call, look at each consecutive pair within that particular this one, what do we call, that particular block actually. In our case, we have went with the this one, this example. So I'll be hard coding the same example within this particular algorithm as well, right? So this is fine. We have to look up at each consecutive pair within that particular block. So that's what we are doing here. The for loop actually, and we have written the if condition. So if the value went up, then we have to set the bit here, set the bit to I minus 1, set the bit from I minus 1 to 1. That's what we are doing here within this particular step. So within the if condition, finally what we are doing, we are storing the plus or minus 1 pattern for this particular block. We are going with the, or we have went with the plus or minus 1, this one itself, right? Plus minus RMQ itself. We are going with the, so all these things we are writing within the plus minus RMQ method itself, right? So this is fine, I believe. Yep, we are done with this part actually. Finally, we are storing the plus or minus 1 pattern for the particular block. So this is fine. Let me delete this. Next, let's move on with the further steps. Yeah. So I'll just scroll this one. Let's move on with the slog part actually. So let's see what we can do. Yep. So just give me a second here. So next we are going with a slog actually. So what we are doing here, so we have to log the table size for nb, the variable nb that we have considered, that we have to do. And slog of 0, we will be assigning this one to the slog of 0, and slog of 1, we will be assigning that one to the 0, right? So this is fine. Where did the slog part go actually? Where did I come? 1 second. So this part actually. So this is fine. The size, we are going with the size nb plus 1. And next we are going with a for loop. For the for loop, what we are doing here, slog of I, we are assigning this one to the slog of I by 2, right? So that's what here we are doing, slog of I by 2. I have written this one in the fancy way by making use of the this one right shift operator, right? So we are assigning the slog of I equals slog of I by 2 plus 1, nothing but floor of log 2 of I basically, right? That's what we are doing. So this is fine within the for loop. Next, we are going with a log nb. So this one is nothing but we are going with a number of levels in the sparse table. If you know the sparse table, you will get to know this one clearly. So we are just going with a number of levels in the sparse table. Finally, we are allocating the sparse table, nothing but level into block here. This one, we are allocating the this one, what do we call, sparse table, nothing but we are going with a level into block. Again, we have went with the 2 for loops. So what we are doing here within the 2 for loops, so within this one we are going with the base case actually. What's the base case accordingly with the exam this one algorithm? So each block is its own range, right? Each block is its own range of 1. The base case that we are going with is nothing but each block is its own range of 1, and we are building the level j from level j minus 1 in the next step, next for loop. Yeah, that's what we are doing. So block with minimum over first half and block with minimum over second half, that we are writing here, right? That we are writing here, right? Finally, what we have to do, we have to pick the block whose representative is smaller. That we are doing within this step. Yeah, that we are doing within this step. So it's as simple as that. Let me delete this one. So now we are done with this part. Let's move up. Let me scroll this one. So we are going with the type here. So this is fine. So types, so the variable types we are considering, because we have to go with the number of distinct, this one plus or minus one patterns possible for the block size b, right? That's completely possible for the block size b. That is the reason we have considered here, right? Again, the prerequisites are, you have to know the sparse table, you have to know the plus minus rmq, right? You have to know the hue and whatever we had discussed at the beginning, actually plus or minus one, right? So Fisher Hune, you have to know that part as well, and you have to have the idea on the Euler. For the further things, you have to have the idea on the Euler as well, and you have to have the idea on so many things actually. Right. So these are some of the prerequisites that I had to mention, or else you'll not understand anything. So next, what? So next we are going with a variable pre here. What is this basically? So pre of pattern into L into R. So basically, this is the local minimum index from L to R, from L to R basically. Yeah, from L to R. So this is fine, I believe. Next, we are going with a this one, the variable done with the type Boolean. So this is nothing but we have to track which patterns have been computed already, right? So for that one, we are going with a Boolean, this one variable done. Yep. So this is fine. Now let's move on with the for loop here. We have to walk every block to populate the this one pre for its pattern, right? For that, we are making use of the for loop. Again, we are just going with some variables here because we have to block the boundaries. So again, so this is fine. So again, we are going with the if condition here. If condition, basically what we are doing within the if condition here, we have to compute this one. We have to compute only once per the unique pattern, right? So that's what we are doing here within the if condition, right? So again, we have written for loop. Again, we have mentioned pre and other stuff within the for loop basically. Why we have written the for loop here? Basically, what we have to do. Um, so we have to compute only once per the unique pattern. So that's what we have done here. So let me delete this one and let's do one thing. Let's move on with the further things. So I'll just move on with the further things here. So let's go with the query index here, right? So let's move on with the query index method here. Right, so within the query, why we are making use of the query index method here? We have to return the global array index of the minimum element in array of left to right. So I can just mention that this one like this, array of left to right. So this is fine, I believe. Yep. Next, what we'll do? Suppose first we have to normalize and we have to ensure L is less than or. So that's what we are doing here. So we have to see which block does left belong to and which block does the right, nothing but the R variable belong to. So that's what we are doing here, this one. And we are going with the if condition here. If condition, because both the endpoints, suppose if both the endpoints are in the same block, right? So for that we have written the if condition, right? So we have to go with the this one direct lookup actually. So we'll be going with block start as well as the local offset of the minimum. Yep. So this is fine. Next, this one actually we are going with this variables. So we are going with the minimum in left as well as the right partial black, right, from the offset, right? So that's what we are doing here. Next, we are going with the best. Best is nothing but best of the two partial block minimums that we had considered earlier, right? So that's what I said. So this is fine. Next, we are going with this part, right? So again, this is fine. We are just going with a range of the complete blocks strictly between the BL as well as the BR here, this part. And finally, for the if condition, so suppose if there are full middle blocks, then what we have to do? One second. So we are going with a QL less than or equal to QR, right? Suppose the range of the complete block strictly between the BL and the BR, that is nothing but suppose there are full middle blocks, the largest power of two fitting in the middle range. So this part, right? So this part, right? So then we have to go with a global index of the minimum among all the middle blocks. So this one mid, as well as we have to update overall best if the middle minimum is smaller, right? So finally we have to return the best, nothing but, so this is the global index of the minimum in A of L to R, right? So this is fine, I believe. This is the step 3, if you remember the algorithm. That's what we had discussed. So this we have written within the method called query index. Yeah, this we have written within the method called query index. Let me delete this one and let's move on with the further things. Yeah, so this is fine, I believe. Let's move on with certain things here. So I'll just go with this what do we call the class Cartesian RMQ. If you remember, so I said we will be making use of the Cartesian RMQ while discussing the algorithm. So that's what we will be doing, right? So just give me a second here. Let's move on with the further things. So this is nothing but the second class. We'll be going with the Cartesian RMQ here. So 1 second, why we will be making use of the Cartesian RMQ again? So basically we will be making use of the Cartesian RMQ to reduce the general array RMQ to the LCA on the Cartesian tree, right? On the Cartesian tree, right? That's the reason we'll be making use of the Cartesian RMQ variable. So this one method, so it reduces the general array RMQ to LCA on a Cartesian tree. So again, so we will be going with the build as well as the query, right? If you remember, I said we will be going with the build as well as the query. Build, so build will be big of n as well as the query will be big of 1. So build will be big of n via monotonic stack that we'll be making use of, as well as the Euler Tour DFS. So we will be going with a Euler Tour DFS as well. Euler Tour DFS as well. And we'll be making use of the monotonic stack. Yeah, monotonic stack. So this is fine, I believe. Next will be query will be big of 1. So this one we know we have already done this one via plus minus RMQ, plus or minus 1 RMQ that we have went with the method that we have already written. The same thing we had discussed till now, right? On the depth array, will be query will be basically big of 1 via plus minus RMQ on the depth array. So this is fine. Now let's discuss this one step by step. What are the variables that we are making use of and why we'll be making use of this one, right? So first thing, we will be going with the array variable. So this is nothing but the original input array. So this is nothing but the n is nothing but the length of the array. So this is nothing but LC as well as the RC that I have used here. So this is nothing but the left or the right child of node I in the Cartesian tree, right? So next we have to go with the Euler Tour, this one, what do we call Euler Tour, as well as the this one, Euler Tour depth, as well as the first. These variables will be helpful within the Euler Tour DFS, right? So this is fine. Next we are going with a this one, what do we call total. Basically total is nothing but the actual length of the Euler Tour, right? It should be basically between 2 and minus 1, right? So it should be not between, it should be 2 and minus 1 if you know the Euler Tour algorithm, right? So this is nothing but the actual length of the Euler Tour, nothing but 2 and minus 1. This one you have to know, you have to keep this one in the mind. Next we are going with a plus minus RMQ variable, this one RMQ. So this one, so this is nothing but again we have the idea on this already. So this is nothing but plus or minus 1 RMQ built on the E depth, right? Built on the E depth or the Euler depth for big O of 1 LCA queries. That's what we had discussed earlier as well, right? So on the depth for big O of 1 LCA queries. So this is fine, I believe. But this part, these are the variables that we'll be making use of within the Cartesian RMQ class. So let me delete this one. Let's move on with the further things. Yeah, let's move on with the further things. So this is the this one, what do we call? This is the constructor part actually, or the initialization part. So let me explain this one in the graph. So brief here. So this one minus 1, so this one you'll get to know array we have assigned this one to a, this is length, so this is fine. So we are going with a minus 1, we are filling all the LC this one with a minus 1 initially, and this one, what do we call, RC with the minus 1. Why we are doing this one? Minus 1 means initially the tree will not be having any child, so that is the reason we are filling the initial values with the minus 1. So this is fine. Next what we are doing, we are going with a stack here. STK is nothing but the monotonic stack that we are going with. So so this is nothing but the monotonic stack of the node indices, and this one we are again we are going with, or we are filling the values of this one, value of the parent with a -1, right? So parent of y is nothing but the parent of node I in the Cartesian tree. So you have to have the idea on the Cartesian tree. Again, if you don't know the Cartesian tree, please do look into the 150 algorithms playlist. Actually, you will find the Cartesian tree there. You can just watch the algorithm and you can just come back here. So as we are going with the monotonic stat, we have assigned this one to the top to -1 as well as the root to 0. Top is nothing but the stack pointer. If you know the stack pretty well, again, if you don't know the stack, so we have discussed the stack as well as the queue, stack, queue, and other data structures actually that is present in the data structures playlist. You can just watch that videos. If you don't have the basic idea, it will be difficult to understand, right? So top equals -1, nothing but this is a stack pointer, -1 initially empty, right? The stack pointer. So top we have assigned this one to the -1, and root will be set at the end. So that is the reason we have assigned the root to 0. Next we are going with a for loop. So we have to process each position left to right. So that is the reason we are going with a for loop, and we are assigning left to -1. Yeah, assigning -1 because last pop node will become left child of the I. So this is fine, I believe. Yep. So then we are just going with a while loop. So while loop, you can just look into the while loop. So nothing but we are popping the nodes whose values are greater than or equal to array of I. So this is nothing but the Cartesian property, right? So this one will be minimum heap by value. So this is fine, I believe. Next, we are moving on with the two if conditions, right? So we are just going with the two if conditions. So if condition last popped, suppose if the last popped is the left child of I, then we will be going with this. We have written the same here. For the second if condition is nothing but, so if we are going with the current stack top, right? So this becomes parent of I. I is nothing but I is its right child, basically the second if condition. And stack of this one top, we have assigned this one to the I. So basically what we are doing here, this one we are just pushing the I onto the stack. So that's what we are doing here. And root we are assigning to the stack of 0. Here bottom of the stack will be equivalent to the overall minimum, right? So that will be equivalent to the root of the Cartesian tree. So that is the reason we have set the root to, or we have assigned the root to stack of 0. Next, let's move on with the further steps, right? So 1 second, just give me a second here. So yeah, let me scroll this one. So we are assigning Euler edep first, as well as the this one we are calling the DFS and other stuff here. So this is fine. Euler is nothing but here. In this case, we are going with the sizes, right? So basically here, Euler tour visits each node 1 plus number of children types, right? So this will be total 2n minus 1. We have already discussed this one. So this is the same thing goes with the depth as well as the first variable, right? So this is fine. Then we are going with the index. We have set this one to the 0. So this is nothing but the mutable counter that is passed into the DFS, right? So, oh, sorry, we are going with the index, right? So index is nothing but the first visit index for each node, right? So this is fine. Then we are calling the DFS. So before moving on with the this one, line number 119 or the 120. So let's understand the DFS part. We have already written the DFS part here, right? So DFS, what we are doing within the DFS, actually, we are making use of the helper method DFS. This is nothing but the standard Euler tour DFS, right? So this is nothing but standard. So let me write here, standard Euler tour DFS. Right, so we will be going with the Euler tour, as I've said. Actually, you have to have the idea on the Euler tour basically. Yep. So we are going with the standard Euler tour DFS here. So here within the DFS, we are recording the node U. We have to recurse into the left child. That's what we have to do, and we have to record U again on return. Yep. And again we have to recurse into the right child as well, left as well as the right child. If you know the Euler tour, record U again on return for the left as well as for the left child as well as the right child. That's what we will be doing within the DFS. So the first thing here, index I of 0. So this one, D, whatever we have written, basically we are recording the position of U's first visit, append the node U to the Euler tree as well as append depth D. That's what we are doing here, right? So then if the left child exists, then we have to recurse into the left child at the depth plus 1. That's what we are doing here. Within this line, suppose if the right child exists, then we have to recurse into the right child the depth plus 1. That's what we are doing here in this line. We have written two if conditions. It's very simple, right? If you know the Euler tour, this one, if you know the Euler tour algorithm, then implementing the same thing will not be a big deal here. Let me delete this one. So this is it for the DFS part. Next, let's move on with the further things here. So after applying the DFS, we are going with the E total as well as the RMQ here, right? So E total, we have assigned this one to the index of 0, nothing but total entries written is equivalent to the 2n minus 1. We have already discussed this one. RMQ, we have assigned this one to the this one. What do we call new? We have called here new plus or minus RMQ. We have already written this method, right? So what we are doing here, basically, we are building plus or minus 1 RMQ, right? So that's what we are doing. That is the reason we have written the method plus or minus this one, plus minus RMQ. Basically, we are building the plus or minus 1 RMQ on the depth array, nothing but depths are this one, plus or minus 1 adjacent here, right? So that's what we are doing here. It's as simple as that. Yeah, we are done with this part. Next, let's move on with the query part. Yeah, next, let's move on with the query part. So what we will be doing within the query part. So suppose, let me tell you why we are making use of this particular method. Yeah, so just give me a second here. Why we are making use of this particular method. So basically, we have to return the minimum value of the array in the range left to right. I can just write here array. So within the array, let me mention a. Yeah, basically what we have to do, we have to return the minimum value of the array in the range L to R. And why we are writing the method, basically the query method, this one, not this one actually, query this one, sorry. So I went with this one. I got confused here. So this one. So this method, we are finding the LCA, least common ancestor of the nodes L and R in the Cartesian tree. That is equivalent to the node with the minimum depth in the Euler tour between the first L, nothing but the first of left and first of right. So that's what we are doing within this particular method. Yep. So let me delete this one. So now, suppose if n equals 0 in the sense, so suppose if we have the empty array, suppose if we have the empty array, then we have to return 0 in that case. Next, we are going with the trivial range here. You can just see L equals a return array of L. That's what we are doing. Then we are going with the Euler tour positions of L and R, right? So then we are going with the Euler tour, this one, positions of L and R respectively. Then we are going with a node at the minimum depth position in FL and FR, this part I'm speaking of, that is equivalent to the LCA, that is equivalent to the range minimum. So this is fine. This is it for the query method. And we are going with a query min method as well. So this is basically the convenience wrapper. I can just call this one as convenience wrapper. So we can just go with a query min. We can go without the query min as well. So it acts as a convenience wrapper. It will be easy for us to understand if we go with a query minimum, right? So we will be sorting L and R left and the right before calling the query. That's what we will be doing within the query min method. Again, it acts as the convenience wrapper here, right? So this is fine, I believe. So we have written the simple if condition. Again, what we are doing, so we are sorting here, we are sorting left and right before calling the query, before calling this query, right? That's what we are doing with the help of the query min method. So let me delete this one. We are done with this part. Next, let's do one thing. Let's move on with this one, compress paste method. So this is one of the very important methods as well. So let me explain what we will be doing here, right? So first thing, so we will be going with this one, compress paste method, right? So what are the things that we'll be making use of? Let's discuss the same here. So here within the compress paste method, actually, first thing, so we have to go with the f of I that is equivalent to the s of 2i plus 1 for the odd. We have to compare with the odd even indices with the this one, odd ranks, right? So if you remember the this one, the different steps that we had discussed during the algorithm explanation by considering the this one example banana. So that's what we will be doing here. F of I is equivalent to the s of 2i plus 1, nothing but first element of pair I, right? First element of pair I, and we have to consider the second element as well, nothing but g of I equals s of 2i plus 2. That's what we are doing here, right? F and g, right? Mx, we have set this one to the 0 because we have to track the minimum value that we have seen, nothing but needed to size counting sort arrays. That's what we have done here. Next, we are moving on with a for loop, right? So this for loop is necessary. Basically, we are going with a character at odd position, nothing but 2i plus 1 in the original string, right? So that's what we are doing within the for loop, right? So next we are going with the 3 for loops here. if you remember, if you see here, we are going with the 3 for loops here. So what are we doing within the 3 for loops? So this is, we call it as first pass. Actually, first pass, we are sorting by G. We are sorting by G. When I say we are sorting by G, we are sorting based on the second element. We are sorting based on the second element. We are sorting with the help of the for loop here, these 3 lines actually. So this might look very this one, what do we call, very difficult, but all we are doing is we are sorting based on the second element here, right? So this is fine. Next, let's move on with the this one, what do we call, uh, again 3 more for loops. So this is nothing but we call it as second pass. So this is, we are sorting, or we are going with the same this one, stable sort by F. This we are sorting based on the first element actually. Yeah, we are sorting based on the first element using the first pass order. So this is using second pass order. So I'll just write it over here, using second pass order, and this one using first pass order. Yeah, using the first pass order. Right, let me delete this one. You can just have a look into the code actually. Yep, so we are this one sorting using second pass order as well as the using first pass order here, based on the second element, based on the first element here. 3 for loops, totally 6 for loops actually. Yeah, so let me delete this one. Yep, so this is fine, I believe. 1 second. Yeah. So yeah, so this is fine. We are going with the resulting variable next. Yeah, we are going with the resulting variable. We have to assign the dense ranks, right? So dense rank. So we are just going with the result variable here. Nothing but the first element in sorted order gets the rank 1. So as we are going with the sorting, actually, the first element in the sorted order gets the rank 1, and then we are going with the result here, result of buffer of 0, that we have assigned this one to the 1. So this will be same rank as previous by default. So the for loop, whatever we are going with, actually same rank. Yeah, same rank as previous by default. If this pair differs from the previous pair, then we have to increment the rank. For that we have written the this one if condition here, right? So finally, result of I. So this one, the result will be stored in the result variable res. So this is equivalent to the rank of pair I in 1 to distinct pairs, right? So this is fine. Next, what we are going to do? Let's move on with the Kasai, right? So we have already discussed the Kasai's algorithm. So we will be implementing the Kasai here. So if you don't know the Kasai algorithm, again, I'm saying you can just go through the 150 algorithms playlist. You can just watch the Kasai's algorithm, this one, and you can just come back here, right? So again, what we are doing within the Kasai method here, Kasai method, it consists of 2 parameters. One is S, another one is suffix array, SA, right? So first thing, we are, suppose if n is less than or equal to 1, we are just returning the new int of 0. What we are doing here, this step basically. So 0 or 1 suffix is equivalent to the empty, this one, what do we call, LCP, this one. Yeah, so this is fine, I believe. So next we are going with the rank variable. So this one we are allotting the size. So this is fine. So we have to invert the suffix array here. So for that one, we are going with this one for loop here. Yep, we are just inverting the SA, right? So suffix array. So then we are assigning the LCP of I, nothing but for the length of the longest this one common prefix between SA of I and SA of I plus 1. That's what we are doing. Again, we are going with one more for loop. We are just iterating over the suffixes in the text order that we have got, right? So here, if condition, because we have to skip the suffix 0 in the sorted order, right? So suppose if we do not have any predecessor, in that case, we have to skip the prefix, this one, suffix 0, sorry. For that, we have written the if condition. Same goes with here as well, right? Finally, we are just storing the LCP between the SA rank of I minus 1 and SA rank of I. So that's what we are doing. And H can only drop by 1 per outer iteration here. This one, if condition that we have written here, right? So total work will be a big of n, right? So total work will be of big of n here, right? So finally, we are returning the LCP, right? So we are returning the LCP. That's what we are doing within the Kasai's algorithm. We are just making use of the Kasai's or Kasai's algorithm here, right? So this implementation is fine, I believe. So this is fine. Let me delete this one. So next, let's move on with the further steps here. Let's move on with the sort even method, right? So let's move on with the sort even. We are done with the left. We have to sort even, right? We are done with the odd. Sorry, we have to move on with the left. if you would have um, this one, if you know what I'm speaking of, basically we had discussed the same thing during the algorithm part as well, or algorithm explanation part. Yep, let's move on with the further things here. Sort even. So what we will be doing here within this particular method, we will be sorting even position suffixes in big of n actually. Yeah, we will be sorting even position suffix in big of n. Suffix at the position 2i is compared as pair s of 2i, right? Pair s of 2i and odd rank of s of 2i plus 1, right? Add odd rank of s of this one, 2i plus 1. We have already discussed this one. So when we articulate the exact same thing, the code might look huge actually. The same thing previous to, if you remember, actually we had made use of this one. We'll be going with this one. What do we call sorting, right? So this we are doing it for the even, right? Rather than the odd, we are doing the same thing for the even. Certain things, there will be change in certain things. So what we will be doing again, what are the changes basically? Suffix at the position 2i will be compared as pair s of this one 2i comma add rank, the odd rank of 2i plus 1, right? So this part. And suffix at this is fine because suffix 2i is equivalent to the suffix s of 2i followed by suffix of 2i plus 1. This we know, right? So and we already know the sorted rank of every odd suffix from the previous steps actually. Yep. So the same thing we are doing here. So let me delete this one. Yep. So this is fine, I believe. So this is it for the basically this is it for the sort even method. Next we are going with the LCP odd. Next we are going with the LCP odd method. LCP odd method, what we are doing. So again, so if you ask me this one, so we are ranking based on the G here and nothing but the second element. Here we are ranking based on the first element. The same thing. Within the previous method we had done the same thing. I don't think I have to explain this one again. So now let's move on with the this one. What do we got? LCP odd. LCP odd is nothing but LCP array for the consecutive odd suffixes in big of n actually. So this is nothing but LCP array, right? So we will be going with the LCP array for the consecutive odd suffixes in big of n, in big of n, right? So LCP between the odd suffixes nothing but SA of odd of I and SA of odd I plus 1 is equivalent to the this formula that we'll be making use of here. This one. You can just look here. This one basically. Yep. So we will be going with a 2 into RMQ of LCP recording, comma, rank in half of I, rank in half of I plus 1 minus 1, right? And plus 1, if the next character also matches, then we have to go with a plus 1, right? So let me delete this one. That's what I have written in the form of code here, right? That's what we have written in the form of code. You can just check this one, this entire method, LCP odd, sorry. Yeah, LCP odd, this entire method basically. Yep, that's what I have written here. So this is fine, I believe. Let me delete this one. Next, let's move on with the LCP even here, right? LCP even, this is similar to the LCP odd. So here the only changes are LCP. So this is for the LCP array for consecutive even suffixes n big of n, and LCP between even suffixes SA even of I and SA even of I plus 1, similar to the odd actually. The only difference is so it will be 0 if the first character this one first characters differ, and it will be 1 plus RMQ of LCP of odd array, the same thing that we had discussed within the this one even as well, right? If the first characters match, right, then we'll be reducing to odd suffix LCP after this one stripping one character, right? So that's what we will be doing within this particular method. Yep, it's similar to the LCP odd itself. So this is fine, I believe. We are done with this part. Next comes the fourth step. If you remember the fourth step actually in the algorithm, we have to move on with the merge method. Actually, we have to merge left as well as the right. That's what we need to do. Let's do that one quickly, right? So merge, let me tell you what we will be doing within the merge method. So I'll just open this one. Just give me a second here. So the first thing here, merge is nothing but we will be merging odd and even suffix arrays. Yeah, we'll be merging odd as well as the even suffix arrays. That's what we will be doing, right? So within the merge method in big of n time complexity, that's what we'll be doing here. So we will be using the LCP credit variables again as per the algorithm explanation that we had went with earlier, right, during the algorithm explanation. So we will be making use of the LCP credit here variables, right? So whether it may be CLO, whether it may be this one CLE, these are the LCP credit variables actually, just to avoid the redundant comparisons. So we don't have to go with the redundant comparisons. To avoid that one, we'll be making use of LCP credit variables like CLO, CLE, right? So here you can clearly see these variables actually. CMP, not this one, CLO, CLE, this one. Yep. So this is fine. If CLO is not equivalent to CLE, then the one with the more shared prefix comes first. Nothing but no character scan is needed here. And if CLO is equivalent to CLE, scan from the depth. Nothing but the amortized big of one total here, right? So that's what we have written in the form of code. Yeah, that's what we have written in the form of code, right? So I can just go through the entire merge method, right? Entire merge method. So this is fine. Yep. So let me delete this one. We are almost done with the merge method as well. Yep. You can just go through the code actually. Then let's move on with the build SA. Build SA is nothing but building the suffix array. Yep. So the main thing we will be doing within the code. So this is nothing but the core Farach recursion or the Farach Silton recursion. So this is where we will be going with the recursion actually, build SA, building the suffix array, right? So let's move on with the further things here. If n equals 1, so we are going with the return new int of 0. Why we are doing this? So this is the base case actually. If we are having the single character, then we have to go with a trivial suffix array. That is the reason we have mentioned like this. Then we are going with the n odd as well as the n even. So we are going with a number of odd position suffixes, nothing but position 135 in our case. If you remember for the odd, for the banana, example banana, we will be, or I have hard coded the same example here within the code. So within the algorithmic code. So the odd here, nothing but 135, and we are going with the n even. N even, nothing but the number of even position suffixes. In our case, for the banana example, we went with 0246, I believe. I remember exactly, it's 0246 itself, right? So this is fine. Then we are going with the SP as well as the SH variables here. What are these variables? So we have to compress the consecutive odd position pairs into the new string of length n odd. That's what we have done here. We are making use of the compress, compress this one pairs method, and we are calling the build SA, nothing but we are going with the recursion here. We are recursing here. So this part is nothing but we are recursing on the compressed string, nothing but suffix array of odd suffixes, right? So that's what we are doing. Next, we are going with the suffix, this one, SA odd. So this one we are going with a for loop here. So this is nothing but we are just going with a rank of the suffix order, right? That's starting at the position P in the sorting order. That's what we are doing here. Again, the same thing. So I can just look into this part as well. And here we are going with the LCP recording as well as the LCP odd A. LCP recording as well as the LCP odd, this one, what do we call odd A? LCP recording is nothing but the LCP array of the recursive, nothing but the compressed suffix array. This we know, this is fine. We are calling the kasai here, right? So we have already written the helper method, this one kasai, and we are calling this one here. We are calling the LCP odd method here, nothing but, so we are going with the LCP array for the odd suffixes actually, right? So this is fine. And next step is we are going the same thing. We are the similar thing actually. We are going with the SA even as well as the LCP even A. So this one is nothing but we are sorting the even position suffixes using the odd ranks, and we are going with the LCP array for the even suffixes, LCP even A, right? So let me delete this one. Let's move on with the further things. Finally, we are calling the merge method here, right? So merge method, what it does, we are merging odd as well as the even suffix arrays using the LCP credits, with the LCP credits. So that's what we are doing here, this part. Yep. So this is fine, I believe. Next, what we are gonna do. So let's go with the build suffix array. This one, build suffix array method is nothing but here we are just going with the public entry point for the suffix array construction here, this part. Yep. So we have called the build method here, right? So we build SA, nothing but we are going with a public entry for this one suffix array construction, and we are going with a public entry for the LCP array as well, right? So it uses the kasai on the first suffix array, right? So that is the reason we are calling the kasai here and build SA method over here, right? So this is fine. Let me delete this one. Now we are done with the algorithm. So algorithm stops here. We are done with the algorithm. Yep. So we have to display the output. Yep. We have to display the output. For that one, we have written the main. We have to display the output in the sense we have to give the input. So I have hard coded the input banana here within the main method, and based on that we have to get the output. So based on whatever algorithm that we have discussed, based on that this one we have to get the desired output, right? So that I have written within the main method. So just give me a second here. Yeah. So here let's discuss the main method very quickly. So we are going with the example banana here. So this is nothing but so string length plus one, whatever I have given here. So this one is nothing but this part. Yep, length plus one. So this is plus one for the sentinel character dollar. Right. So we have went with a unique terminal or the sentinel character dollar. Right. So this is plus one for the sentinel character dollar, right? So then this is fine. So we have to encode, right? So for encoding, so this one str.char1 hyphen a plus 1. So this is nothing but the ASCII. So we have to encode a equals 1, b equals to 2, n equals to 14, right? So n a1, b2, c3, d4, like that. N will be equivalent to 14. We will be shifting by 1. So sentinel 0 is less than equivalent to less than all the characters. So that's what we are doing here. S of n minus 1, we have set this one to the 0, right? So why we have set this one to the 0? So this is the lexicographically smallest. So this guarantees the unique suffixes, basically. That is the reason. So this part, this is simple. So basically we are building the suffix array of banana by calling the build suffix array, and we are calling the build LCP array using the Casais. Basically we are building the LCP array using the Casais. So we have to show that one in the form of output, right? So that is the reason we have called build suffix array as well as the build this one LCP. So this is fine. Next we are going with the expected suffix array and expected LCP here, right? So this one expected. So this is nothing but the ground truth. So ground truth for the suffix array for the banana, for the example that we have considered, banana followed by the unique terminal or the sentinel dollar, and this is the ground truth for the LCP for this one. What do we call banana? Of the same thing actually. The string that we have considered. So this part is nothing but 1 second. This part is nothing but yeah, this system out println and whatever we are going with, we are just printing. We have to print certain things. That is the reason I have made use of the system out println basically, right? So we are printing and verifying the suffix array. This part actually. 1 second. Yeah, this part we are printing and verifying the SA or the suffix array, and we are printing and this one verifying the LCP array as well. Yeah, verifying the LCP. So this is fine. Next, we are going with the system out println. So this part actually, what we are doing here, this is nothing but the table header to make this one output look good actually. Within the terminal we are going with this part. Yeah, so this is nothing but the table header. And yeah, so next what we are doing here, this one within the for loop, what we are doing here, so we are so the first part we are reconstructing the suffix string for the display, this part. So let me show this one entirely. So I'll just move this one. Yeah, what happened here? Yeah, this one you can just pause the video and have a look into it. What we are doing here, string suffix equals this one, whatever we have written in the for loop. So we are reconstructing the suffix string for the display, and we are going with the LCP equals 0 here. LCP of 0, sorry, this is undefined, right? So no previous suffix, plus we have to show this one hyphen here. We are just showing the hyphen. And finally what we are printing here, so we are printing the row. In the row, what are the things that we are printing? Basically rank, suffix array, value, LCP, as well as the suffix text. These are the things that we are printing here, right? So within this one, that's what we are doing here. So this is it for the main method. This is it for the main method. And with the algorithm, this one, what do you call? This might you might feel this one very large actually. Basically, if you this one segregate this one into correct things actually, different methods, understanding this one will be easy. So if you know the Casais algorithm, the implementation becomes easier, and sorting the even and odd, we have the idea actually, no worries. And we are compressing the pace. We went with this one step by step. We have this one idea actually, the compression part. So Euler DFS, so you have to have the idea on the Euler tour actually algorithm, so that we know actually this becomes easier if you have the idea on the Euler tour as well, right? So this is one thing. And what are the methods that we have made use of? So Cartesian RMQ for the plus or minus one. So for that one, we have the idea plus or minus one RMQ. So we are going with the Cartesian RMQ, and we have written the method plus minus RMQ as well, right? So that also we have the idea, and we have the idea on the query as well as the this one query min as well as the query index, right? So that also we have the idea. So everything whatever we have made use of, actually starting from the plus minus or mq query index, right? So Kasai's algorithm, you have to have the idea. Euler tour, yeah, Euler tour, you have to have the idea. So it is the, if you segregate it properly, so each algorithm, if you know, then the implementation becomes easier. So I'm not saying entire thing is easier, no. So this Farach implementation is difficult. Actually, you have to know the different algorithms. You have to have the idea on the different algorithms. That if you have the good understanding of the different algorithms that we are making use of within the Farach implementation or within the pure Farach algorithm here, so then the implementation becomes easier, right? Then you can just understand it easily, right? So I'm not saying the algorithm entirely is easy. No, it's not easier. This one Farach implementation is not entirely easier. It's the difficult one. Actually, you have to have the idea on the different algorithms. If you have the idea on the different algorithms, actually, then the implementation might find easy. You might find the implementation easy, or suppose if you go with a hard-coded example, then you might find it easier, right? If you um, segregate into different methods or the different steps, and then you try to understand, it becomes easier, right? Step always, I would like to say, always segregate certain things into the different methods or the different steps, then try to solve. Then try to solve, whether it may be problems, whether it may be even the algorithms as well. If you don't understand the algorithm, just try to this one go with a hard coded example, and just try to understand the algorithm with that particular example. Now you have hell lot of resources to go. Resources are in plenty. All you have to do is you have to have this one, the zeal to learn. That's it. Nothing else, right? So so this is it for the Farach algorithm, right? So this is it for the Martin Farach Silton algorithm, or else we call this one as Farach Silton and Benda algorithm. That also we do, right? So let me run this one. Yeah, see here, we are getting the this one suffix automaton. Sorry, not the suffix automaton, suffix array basically, which is correct. Uh, 653102. So this one we have hard coded actually LCP. This one we are getting correct actually. So based on the boolean this one method that we have written, right? So that one, so we are getting true here, right? So this one is correct actually. For the example that we have considered, suffix array as well as the LCP is true, 653104 and 013002. So for the example that we have considered, the suffix array as well as the LCP is true, and we are displaying the table as well. So this is nothing but the this one iteration starts from the zero indices 0, 1, 2, 3, 4, 5, 6. This is nothing but the suffix array of I. This is nothing but the LCP of I, and this is the suffix. You can clearly see we have discussed this one already during the algorithm part. Yeah, for that we have written the different methods. Actually, we have segregated this one into the different methods, and we have tried this one to we have tried to understand actually. Yep. Yeah, so this is nothing but the index, this is nothing but the suffix array of I. So the same thing actually, 653104 we have to get here. 653104, we have got this one in the table, which is absolutely correct. That is the reason it is showing true here. And so this is nothing but the LCP of I. We have to get 013002. We have got 013002. Initially it will be null, so hyphen, right? Suffix they have mentioned here, right? Suffix, we have got the same thing. This is nothing but the sentinel dollar a sentinel a sentinel. So this one I have already shown you, right? So during the algorithm explanation, right? So finally BANA followed by the sentinel character, NA followed by the sentinel character, NA followed by the sentinel character, right? So this is it for the output part. We are getting the desired output. The suffix array and the LCP array that we are getting is absolutely correct, right? Suffix array it is showing true, and the LCP array we are getting true as well, right? Suffix array nothing but 653104. LCP array is nothing but the this one, what do we call, 013002. So this is fine, I believe. We are done with the algorithm part. Next, let's do one thing. We are getting the desired output, right? So based on the code that we have written, we are getting the desired output. Now let's do one thing. Let's quickly discuss the complexities for the code that we have written. Yeah, let's do that. So what will be the time complexity here? You would have already guessed the time complexity would lead to big of n, right? So the naive approach would lead to usually big of n square log n. Basically, we are this one. What do we call? Yeah, we are reducing that one, this one from big of n square log n to big of n, from the brute force to this one big of n by making use of the Casais algorithm. Sorry, not Casais algorithm. Basically, Farach-Silton algorithm. We call it as usually we call it as Farach's algorithm, right? So this is fine. The time complexity would lead to big of n because we are going with the recurrence, and the recurrence be we can just express in this way: t of n equals t of n by 2. Yeah, t of n equals t of n by 2 plus big of n. Yeah, so the recurrence is nothing but t of n is equivalent to t of n by 2 plus big of n, right? So the compress, the sort even that we are going with, the compress, the methods that we have went with, if you remember, we are going with a compress, we are going with a sort even as well. We are going with a sort even, we are going with the LCP method, yeah, and we are going with a merge method as well. Yeah, we are going with a number of methods. So these are the methods of the functions that we have went with: the compress, sort even, LCP, and the merge steps all run in the linear time via radix sort. So we are going with a radix sort itself, basically. Yeah, we are going with a radix sort itself. So during during the explanation, we had went through the sorting. So basically, the sorting steps we have made use of the radix sort itself. If you know the radix sort, so it will be easier to understand. Anyways, so now we have went with different methods, namely compress, sort even, LCP, as well as the merge steps, all run in the linear time via radix sort. And also we have went with the this one, what do we call, Cartesian tree, right? Cartesian tree method as well, right? Sorry, Cartesian tree method as well, right? So Cartesian tree RMQ. Again, let me say this one. The compress, sort even, LCP, and the merge steps, or the merge methods or the functions, all run in the linear time via radix sort as well as the Cartesian tree RMQ, as well as Cartesian tree RMQ. So this is fine, I believe. So this is it for the, what do we call, time complexity part. So basically it's big of n. So overall we can just consider big of n actually. Yep. So what will be the space complexity then? Space complexity would lead to big of n as well. So why it is big of n? So we are going with a Euler tour, right? So Euler tour, this one entries, it would take this one 2n minus 1, right? So it takes because sorry, not the big O actually, it takes 2n minus 1 entries. So we are going with a sparse table as well. The log 2 actually initially we had discussed on the same thing, right? So the sparse table is big of n log n. Yeah, sparse table takes big of n log n. But first thing that we went with actually, yep, this one plus r plus minus RMQ. That is nothing but the so I had said that it is nothing but the Fisher-Hune, right? So we are going with a Fisher-Hune this one method. Basically, we have implemented the Fisher-Hune pre-computed blocks, Fisher this one Hune pre-computed blocks that would take big of n. That would take big of n. Sparse table big of n log n. So this one Fisher-Hune pre-computed blocks big of n, and the Euler tour takes 2n minus 1, and the Euler tour takes 2n minus 1 entry, right? So 1 second, yeah, and the Euler tour takes 2n minus 1 entry. Sparse table big of n log n. This one, what do we call, Fisher-Hune pre-computed blocks big of n. Yeah, so I'll just write here Fisher-Hune FH, and this one nothing but the Euler tour. Yeah, Euler tour entries 2n minus 1, right? So this keeps overall space linear. So overall space complexity would lead to big of n as well. So the time complexity and the space complexity for the code that we have written would lead to big of n and big of n respectively. So this is the overall time complexity and the space complexity for the code that we have written. Right? Usually, if you go with the naive or the brute force approach, actually, it will be big of n square log n. We are reducing that one drastically from big of n square log n to big of n. Yep. So that's what we are doing by making use of the Farach-Silton and Bender algorithm, or Martin-Farach algorithm. So yep. So this is it for the Farach algorithm. So let me delete this one entirely. 1 second. Yeah. So this is it for the algorithm. And we have got the desired output as well. And we have discussed the algorithm as well. So first we discussed the definition as well as the algorithm, this one part, or the algorithm explanation or the approach part. Then we discussed about the code and we got the desired output. When we ran the code, we discussed about the code step by step, and we ran while running the code. We have considered the hard coded example banana, and we have this one got the desired output as well, right? So here you can clearly see we have got the desired output, the this one suffix array as well as the LCP array. We have got the desired output. So after getting the desired output, we have discussed the complexities part as well, right? So we are done with the algorithm part. Yep, we are done with the algorithm part, and this is going to be the last algorithm in the string complex or the hardcore string techniques or the string algorithms. So this is going to be the last algorithm, right? So if you find this one very this one difficult, or it is extremely hard to implement, you can just go with the DC3 or the skew. That's also one of the algorithms that you need to know. Implementation, that's quite heavy as well. Not heavy as this one. Not heavy as this one. What do we call Farach's algorithm, right? It's a bit heavy. Algorithm is heavy. DC3 or the skew algorithm is also a bit heavy, but it's simpler. It's simple. Uh, it's yeah. It is simple compared to the Farach algorithm. It's not entirely simple. It's difficult to implement as well, but it's simple compared to the Farach algorithm, right? So both does the same thing actually. It reduces the time complexity drastically. You can just check the this one DC3, we call it as DC3 or the skew algorithm. You can just check that one as well, right? So I insist you to check one. I insist you to check on the same actually, Forest or the this one. What do we call? Sorry, not the Forest actually. DC3 or the skew algorithm. Yeah, you can just Google it and you can just go through the algorithm. Yep. So I believe Forest Silton algorithm is completely clear, right? So for now, this is it. Thanks for watching, guys.